Beijing in China. One of the biggest cities in the world, where demand for air travel is soaring. But the city's only airport has reached breaking point. New York-based architect Wendy Fock has traveled to Beijing to see how the designers and engineers here are attempting the impossible.
The current airport is at capacity. It was originally intended for 76 million passengers each year. But it's operating well above that. Last year alone, 100 million people passed through its doors. This is a serious problem. This cannot go on. It's causing problems for flight reliability, passenger experience, airline operations. Beijing is in real need of a solution.
With passenger numbers predicted to rise even further, the pressure on the airport is only going to get worse. "2,000 years ago, travelers would have come to Beijing by the long and windy silk trade roads. In 1272, the Tonghui Canal was dug, so boats could sail directly into the city, just in time for explorer Marco Polo's first visit.
Ciao!
By 1910, Beijing had a rudimentary runway for travelers to arrive by air, the first airport in China. Since then, air travel has grown and grown, but with 21 million people living in the city, the current airport just can't cope. The solution the engineers in China have come up with is stunning. This is the brand new Beijing Daxing International Airport. Currently under construction, it's set to become the biggest airport in the world. Wendy is getting the chance to see it before it opens to the public.
Wow, I cannot believe how high the ceilings are. All of those dips and swirls are super amazing.
It's very beautiful, very big, so exciting to see such a huge terminal here in China.
This airport is a benchmark for airport construction. We use a lot of cutting-edge technology to make this impossible project possible.
I feel like an ant in this gigantic structure. Super grandiose, and you can barely even see how the structure is done. It's really well designed. Barely see any columns here. It's really amazing what the engineers have done here.
Occupying more than 45 square kilometers, Daxing Airport's site is 2/3 the size of Manhattan. The spectacular star-shaped terminal covers 700,000 square meters, with a massive roof constructed from 52,000 tons of steel, equivalent to 500 steam engines. By the time the entire project is fully completed, it will include a record-breaking 6 runways and could see 100 million travelers every year. But with the old airport at crisis point, constructing this immense terminal is a race against time.
我认为呢，航站楼最大的难点。
Wendy is finding out more from Deputy Engineering Manager Go Aiping.
建设工期只用了3年零9个月。
So Mr. Gao is saying they need to build this entire terminal in 3 years and 9 months. That is an incredibly short amount of time to build an airport.
Rapidly laying the groundwork for this extremely complex megastructure was the first step.
我们在虎林
So Go and his team came up with an innovative solution to speed up construction.
就用这小火车用到中间来的。
So the engineers constructed a temporary railroad system to the core of the building to bring the materials to get distributed around the building to move the materials really quickly.
16 wireless remote-controlled trains transport up to 25 tons of construction materials, helping make the build 4 times faster.
How many people are making this project possible?
我们在施工的高峰阶段，航站区总人数近2万人。
Oh wow, that's actually pretty amazing. At peak times, there's about 20,000 people working on this project. And you could actually see there's a huge amount of people just working on different parts of the construction right now.
With this vast workforce, it's hoped this entire terminal can be completed in record time. But first, there are still major engineering obstacles to overcome. How do you move millions of passengers through the airport efficiently? How do you build the terminal's colossal, intricately curved roof? And most crucially, how do you protect the airport from devastating earthquakes?
I think this is one of the most structurally impressive engineering projects in the world.
Beijing's current airport is under tremendous strain. With China on track to become the biggest air traffic providers on the planet, the situation is critical. The solution? The new Beijing Daxing International Airport, set to be the largest in the world, with a terminal of epic proportions. At 700,000 square meters, the building is equivalent to 149 Royal Albert Halls. With high-speed train and metro links, this is the world's largest integrated transport hub. But before this astonishing structure could be built, there's a crucial challenge with the design that needs to be solved. New York-based architect Wendy Fock has special access to visit the airport site.
Getting to your gate at the airport sometimes is an impossible feat. You sometimes get lost, you don't see the signage, and sometimes you're just rushing in general. For a huge airport like this, to get over 72 million people through its gates, it's going to be super difficult.
Designing the airport to guide passengers through it is something that engineer Wang Chung has to solve.
If people cannot find the right direction, it will cause chaos in the terminal. So it's really important to get it right.
But it's an exceptionally difficult problem for engineers.
Passengers are unpredictable. Sometimes passengers will make mistakes, so we have to provide different passenger routes however they come. It's an extra challenge for the designer.
So how do you move people around the airport efficiently? To find the answer, the team will need to draw inspiration from the pioneers of the past.
This is Midtown Manhattan. It's the heart of New York City, the largest city in the United States, and by virtue of being a place where everyone wants to be, one of the busiest cities.
Architect Cara Michelle is investigating how her 19th century predecessors dealt with a sudden increase in demand for public transport.
So it was an incredible challenge for the early architects of New York City to figure out how to get people onto and off of the island, especially during a time of unprecedented population growth. So figuring out a solution for how to transport both regular commuters and long-distance travelers on a daily basis was really difficult.
A massive new transport hub would need to coordinate the smooth movement of people through it on a scale which had never been attempted before. Architects Whitney Warren and Charles Reed took on the challenge of designing a new train terminal. And their solution?
This is Grand Central Terminal.
The largest railway station on the planet.
One of the things that makes the main concourse so incredible is the sheer scale of it.
750,000 people pass through daily. Warren and Reed came up with ingenious ways to ensure they didn't get in each other's way. This could prove instrumental to the engineers in Beijing.
First of all, you enter the main concourse and you immediately see this information center, but you can also see the location of the tracks. You understand immediately where you need to go. You know, that is really accentuated by the fact that there are no interior columns breaking up this space. It's really an open plan.
No columns meant a passenger's view of signs was not obstructed. But there was still a major problem. Usually stations had stairs, which slowed people down and created bottlenecks.
So these ramps really represent one of the major design innovations in Grand Central Terminal. But one of the things they had to work on was determining what the right gradient would be. And they actually built a number of models and tested them out to determine what the right slope is for people carrying luggage and even people of a variety levels of fitness and ability, to make sure that it was, just subtle enough for people to feel comfortable, but also the right slope to effectively and quickly move people in and out. So let's see. It looks like we're getting something between 5.5 and 6 degrees of slope, which seems about right.
Grand Central Terminal was the first station to use ramps on a large scale. They're far more efficient than using stairs or even escalators today.
Another one of the many innovations in Grand Central Terminal is the fact that the tracks are actually on 2 levels.
Usually, rail tracks are laid out in a row. But with 43 platforms at Grand Central, that's a long way to walk. By splitting the tracks over 2 floors, it's less distance for passengers to walk. And there's another benefit.
So you have long-distance passengers who need a little bit more time to get on the train, have more baggage on the upper level. And then you have short-trip commuters on the lower level. And another innovation is looping tracks. So they're actually dropping passengers off on one platform and then looping around to board departing passengers on another platform. Every piece of the design and architecture in Grand Central Terminal is really focused on getting people moving more efficiently and more quickly through the station.
Grand Central Terminal is a world first. Despite being built in 1913, it still works brilliantly today.
So what Warren and Reed accomplished here over 100 years ago truly revolutionized the design of transportation hubs. And it's a wonder to think that designers of transportation hubs all over the world are still looking to this space to understand how to effectively move people around. I mean, it's really a marvel and a monument, almost a cathedral, to good engineering.
In China, engineers have built upon Warren and Reed's groundbreaking designs to create this cutting-edge 21st century airport. Instead of having the 79 departure gates in a row, they came up with an ingenious way to compact them and reduce walking times.
The shape of the building is like the hand. We have 5 fingers or 5 piers. And also we control the size of the terminal. From center of the terminal to the furthest gate, it's just 600 meters, which means it will just take you 8 minutes to go to the furthest gate. It's excellent considering the size of the terminal.
To help people spot their gate quicker, engineers used another strategy.
We create open space in the terminal, and for passengers, it's very easy to find the gate signs in this kind of open space because there's no columns, no barriers to block the sign.
Just like at Grand Central, Daxing Airport is engineered to keep different types of travellers separate so they don't get in each other's way, whilst ramps and travelators help keep people moving.
This is the center pier, is for the international flights. This side, the two piers, is for the domestic flights. The other side is two piers, is also for the domestic flights. And passengers from check-in counter to the gates, they always go down with one clear, efficient direction to optimize the passenger flow.
In preparation for the airport opening, engineers are rigorously testing passenger flow with the help of 51,000 volunteers.
So here we go. We're going to try to test this out.
And today, New York-based architect Wendy Fook is getting the chance to put the design through its paces.
We're actually walking towards the international gates. If I were trying to get to a flight, I would be super nervous right now.
It should take a maximum of 8 minutes to get to the furthest gate.
We're doing a good job right now. See behind me this beautiful Chinese garden that's still in construction. And we're close to the end of the terminal. So here we are at the end of the terminal. We've made our flight. Despite being such a huge airport, took less than 6 minutes. That's under what the engineers estimated. That's pretty incredible.
Coordinating the movement of a potential 100 million people a year is a massive achievement for the engineers of one of the largest terminal buildings ever constructed. The Daxing Airport buildings cover 700,000 square meters. When finished, the 6 runways will accommodate an astonishing 880,000 flights per year. In China, air travel is booming. To cope with the increased demand, something exceptional is needed. So engineers are building the Beijing Daxing International Airport, a cutting-edge transport hub on a scale never seen before. Handling 880,000 flights a year, the terminal is constructed on the world's biggest seamless slab of concrete, which at 180,000 square meters is more than 7 times the size of Rome's Colosseum.
I think it's a beautiful structure.
Architect Wendy Fook has been invited to explore the airport before it opens.
Personally, I really love how the span of this entire building is actually from a center point. It's really cool. I think the structural engineers did an amazing job here.
Constructing a single terminal building on such an unprecedented scale was a huge challenge for engineers like Lei Su,
Be careful here.
who has special access to one of the project's biggest challenges. The enormous roof.
The roof is very big, we can see. The area is 180,000 square meters. It's one of the biggest terminal roof in the world. It's not only a structure, it's like a piece of artwork.
The artistic roof is an extremely complex shape with multiple flowing curves.
It's very difficult to build this kind of roof because the curves have different direction, and from the high point to the lowest point, the height difference is almost 27 meters. Building this kind of roof is the biggest challenge of the terminal construction.
The problem was made even harder by the need for an unobstructed space inside the airport.
In order to make much more space inside, we cannot put too much columns inside of the building. So how can we hold such a big roof with less columns?
A traditional concrete and girder roof would be too heavy. So to solve this seemingly impossible challenge, engineers would need inspiration from the pioneers of the past.
We are in Split, very old, beautiful Mediterranean town. We believe that we are the sportiest city in the world.
Architect and sports fan Dinko Pericic lives in Croatia in southern Europe. In 1979, Split was chosen to host the Mediterranean Games, and the pressure was on to build a world-class arena.
One of the biggest challenges was to make an athletic stadium for 55,000 people in the audience, and the design of the stadium had to be something really special. The games were held during the summertime, so it would be definitely too hot for spectators. So the roof had to be built to protect them, and it was important that the roof doesn't have supporting columns. They would block the views, so it was a big challenge.
And what engineers came up with is awe-inspiring.
Here we are, Sports Stadium, Poljud in Split. Yeah, this is a wonderful piece of architecture, wonderful piece of engineering.
These massive steel roofs are each 220 meters long, covering a combined area of more than 13,000 square meters.
When it was built, this was the largest curved roof of this kind in the world.
These long-span roofs wouldn't have been possible without Alexander Graham Bell. Famous for inventing the telephone, in 1902 he became interested in flight and made huge wings of interconnected pyramids. The technique became known as a space frame. And Dinko has a unique opportunity to take a closer look.
Yeah, here we are in the roof. This is a space frame construction. This is a structure that normal people can feel just from below. You see that there are no columns supporting you. There is just air below us. I have to hold my helmet that it doesn't fall down. Here we have those triangular pyramids made out of 12,000 poles and more than 3,500 balls, creating this shape, this spatial structure.
Pyramids are very strong in all directions because they spread forces evenly. And these frames don't need much material to build them, so they're also very light. Space frames are made of straight poles, but this roof has multiple curves. To show how this is possible, Dinko is building his own space frame.
And this is a very lightweight structure. This space is mostly air. There is just a minimum material. The story becomes interesting when we start to multiply these elements. We can simply connect them together and get a chain of pyramids, which is actually creating a spatial frame.
To make this roof curved, engineers made some of the poles longer and changed the angle of the connections.
By simply introducing longer poles, we get a curved structure. It's almost like a fabric, which can be very flexible to work with. In these two roofs, there are more than 1,000 different lengths of poles and more than 1,500 different connections. But to calculate each of those elements, it's really complex.
For decades, calculating the thousands of different elements required for a multi-curved roof was thought impossible. But advances in another field provided a breakthrough.
So this roof of this stadium was the first one where computers were used to calculate these specific elements.
Using computers here proved space frames could form almost any shape long-span roof. Essential for the engineers in China.
70 years after Alexander Graham Bell invented his space frames made out of triangular pyramids, it was used in a very creative way here in Polju, in this stadium. I'm really proud that I'm part of this culture that was able to construct something like this.
Engineers in China have taken the space frame innovation and created a roof 13 times the size of that on the stadium in Croatia. This jaw-dropping structure that makes this terminal roof possible is completely hidden from passengers. But Lei Su has permission to see it up close.
We are in the steel structure of the roof. We have 63,000 posts like this, and we have 12,000 bolts here like that. We use steel structure so it can meet the stiffness, but it's still very light.
With the help of computer design, these poles and balls could form the complicated multi-curved roof.
We have many kinds of curve, so with the ball and the post, it's easier to meet a different shape of the design. So all the posts and the balls, we are in different sizes. Some are long, some are short, and some are big, and some are small.
With 75,000 individual parts, assembling this supersized roof could be a big challenge.
Because we have many kinds of posts and balls, we use a new technology. We put the QR code on each of these pins and the balls. So with this, we use a mobile phone to scan in the QR code, and we know where the ball and the pole exactly to be on the roof, and we can put it together very smoothly.
Once the basic shape of the terminal was in place, the complicated space frame roof could be built. First, 8 huge columns are made. Then the gigantic roof is constructed in several segments.
We weld the toe and the balls together on the ground and lifting it.
Each section must be positioned precisely, with 2mm accuracy. Any error could jeopardize the stability of the whole structure.
We joined the section together and formed one big roof.
The center section is lifted last, completing this astonishing space frame.
It's like a steel forest. It's very beautiful. You can see a lot of posts like trees.
Inside, cladding is added, which dampens the noise in the terminal. On the roof, 8,000 panes of glass make the skylights. And 40,000 sections of sparkling aluminium cladding finish this incredible structure.
The steel structure is the biggest challenge of our terminal construction. What most impressed me is how fast we built it. I'm proud of it.
Visiting architect Wendy is taking in this gravity-defying marvel.
For me, I think the roof structure is just absolutely incredible. You can barely even see any of the columns. Especially standing in the center point, you could really see everything from here.
The colossal roof needs just 8 columns to support it, which is only possible because the space frame engineering allows such long and lightweight spans.
I think it's actually incredible that so many components were brought together to make this gigantic roof system. It required so many innovative systems to really put together the different pieces of the roof and then joining it with such precision. This is truly one of the most remarkable roof structure that I've ever seen.
Engineers in China are attempting to achieve the impossible. This is the Beijing Daxing International Airport, a futuristic engineering marvel, on track to be the biggest airport on the planet.
The way that it's constructed is truly amazing. I think it is really remarkable that the engineers were able to make this happen.
Across the new airport site, 1.6 million cubic meters of concrete forms the runways and base of the massive 7-story terminal. Its steel roof weighs 52,000 tons and is held up by only 8 columns. Engineers must now take on one of the most serious challenges of the project.
Beijing is located in the earthquake zone in northern China. In history, there are some major earthquakes happened in this place.
It's a life or death problem that falls on engineer Wang Cheng and the design team to solve.
It's really important to protect the terminal from earthquake. There are tens of thousands of passengers and staff in and out the terminal every day. Secondly, after earthquake, the airport is usually the lifeline for the rescue supplies and personnel.
It's common for Beijing to have earthquakes of 2 or 3 on the Richter scale, but they can be much more severe.
It is a huge terminal. To protect it during earthquake is very difficult. This is one of the biggest challenges we have to solve.
During a devastating earthquake, how do you ensure this vast transport hub is protected and remains operational? To solve this critical problem, engineers must look to history's ancient innovators. Archaeologist Gabriel Zoftriegel is investigating an ancient Greek settlement, which could help the engineers in China.
We are in Italy, south of Naples, but the site we're looking at is actually a Greek site because the Greeks founded colonies in Italy, and one of them is Paestum, which was a big city founded around 600 BC.
But building in Italy is difficult. It's one of the most seismically active regions in Europe.
We had some major earthquakes in recent years, and we saw that many modern buildings collapsed. What we see on some classical sites like Paestum is that there's still buildings standing from 2,500 years ago, and you ask yourself, how is it possible that these buildings have resisted for so much time?
Ancient Greek civil engineers were master temple builders, and many have survived to this day. These are the stunning temples of Paestum.
We have 3 Greek temples still standing here, and the biggest one, the Neptune temple, it has 6 columns on the short sides, 14 columns on the long sides, 5th century BCE, still standing. An extraordinary example of Greek engineering because it resisted all the earthquakes.
Coming from a highly active earthquake zone themselves, the ancient Greek engineers had an ingenious way to tackle the problem.
While the foundations are very, very solid, the columns are much more flexible. And you see they are built of several pieces, we call them drums. They didn't use any mortar, and so it's not rigid, solid block, but it's pieces, one piece sitting on the other, so they can move and swing up to a certain degree. And as soon as you have more than one element, the behavior of the column changes.
Building columns from several drums without mortar was crucial to these temples' ability to resist earthquakes. It's a technique that could help the engineers in Daxing Airport.
We have here our column, but it's one piece. We glued it all together. So when we have an earthquake, we see that it shakes, it behaves as one piece, and you have a high concentration of energy here, and then it eventually collapses. The movement of the earthquake is totally transmitted to the top of the structure.
But the column drums in these temples are not stuck together with mortar. So Gabriel is repeating the experiment with separate blocks.
And look what happens if you don't have one rigid piece, but a column built of several pieces. And now the earthquake comes and you see that I can put in more energy and it still doesn't collapse. And you can see how it opens and closes the single element. And basically each element absorbs energy, so much less arrives at the top than what the earthquake gives in at the bottom. So this is the original ancient Greek damper and isolation system.
This isolation method provides astonishing earthquake resistance for these monumental temples.
This structure has been standing for 2,500 years. This is really a great achievement.
At Daxing Airport in China, engineers are using similar principles to the early Greek temple builders to protect this pioneering terminal from earthquakes. But here, it's on a much bigger scale.
So right now we are at the basement first floor under the terminal. Look at the pillar. On the top of it, we install a isolation damper. The isolation damper is like a spring or rubber to protect the terminal from earthquake. Usually there are two kinds of movements during the earthquake, horizontal and vertical. And for the building, the horizontal movement is the most damaging. So the damper lets the building move forward and come back to the place where it was to release the horizontal earthquake energy.
The dampers are made from a stack of 30 rubber and steel discs on a spindle. Like the stones in the Greek columns, they're not stuck together. In an earthquake, instead of holding the building firm, they let it move horizontally back and forth. This dissipates the energy, isolating the terminal from the earthquake. They also have another surprising benefit for this unique transport hub.
The train will go through the terminal, which will cause vibration, and the damper can prevent the vertical vibration. So the passenger in the terminal will feel very comfortable and quiet with no noise.
Throughout the site, 1,152 base isolation dampers were installed on top of the pillars. The finished terminal can safely withstand earthquakes up to 8 on the seismic intensity scale, making it the largest anti-seismic building in the world.
I think it is one of the biggest achievements in this airport.
Now, close to completion, New York-based architect Wendy Fock has privileged access to the airport construction site.
Considering how massive this airport is, I think it's incredible that the engineers were able to find a way to make this entire terminal earthquake-proof. I think that's something that's truly remarkable about this project.
This entire terminal has been built in just 3 years, 9 months. A stunning achievement for an airport of this size.
This is so amazing. This structure really just boggles your mind on how many pieces and how many people actually made this possible. It's truly an engineering phenomenon.
This immense superstructure is an engineering masterpiece. Combining the skills of designers and engineers from around the globe.
At the moment, this terminal is one of the biggest engineering projects in the world. And I was so excited to work here.
For the team behind this astonishing project, the achievement is immeasurable.
In this terminal, I like the open space and the beautiful curve, which will inspire other airports.
This mega airport site is more than 45 square kilometers. The terminal is the star attraction. With 7 floors and a 52,000-ton multi-curved roof, it will run 880,000 flights a year. It's the world's first airport to have high-speed railway, subway and airport express trains all passing beneath it. Now complete, the Beijing Daxing International Airport is becoming a vital transport hub for 100 million people every year. The terminal combines breathtaking design with cutting-edge engineering.
This is actually one of the most beautiful airports that I have seen. Projects like this push the boundaries of what construction really could do.
When it comes to the terminal, I feel very proud. I have been an engineer for 16 years. This is the biggest and the most important thing I've ever done.
Inspired by the pioneers of the past and overcoming complex challenges, engineers have pushed the boundaries of architecture and construction.
When I come here to take flight with my family, I feel very exciting and very proud.
And they've succeeded in making the impossible possible.